Hello, welcome to Introduction to Rheology. I cobbled this presentation together from various sources. I'm going to narrate it. By that I mean I'm going to read it all aloud rather poorly. I haven't rehearsed this, so you can enjoy that. Although for the most part you can just read the slides. Rheology, the science and study of the deformation and flow of matter. It's also used to indicate the properties of a given fluid. Rheology is an extremely important property of drilling muds, drill-in fluids, workover and completion fluids, cements, and specialty fluids and pills, and fracturing fluids. Rheology describes the relationships between the shear rate and the shear stress, or the flow rate and the friction pressure, that causes movement. Flow of fluid in a pipe. When a fluid is pumped in a horizontal pipe that has a constant inner diameter, the pressure increases linearly along the pipe from its outlet up to the pump itself. This friction pressure is due to frictional effects between the various layers of fluid, and between the fluid and the pipe walls. As pressure is applied to a static fluid in a pipe, the fluid will begin to flow in a laminar regime, pass through a transition phase, become a turbulent flow regime, as is illustrated to the right. The two main flow regimes are laminar and turbulent. Laminar flow, a type of streamlined flow for single-phase fluids in which the fluid moves in parallel layers, or laminae. The layers flow smoothly over each other, with instabilities being dampened by the viscosity. Laminar flow occurs in straight pipes when the Reynolds number is below a critical value. Above this value, the flow is turbulent. In laminar flow, the particles of fluid in contact with the wall have a velocity of 0. The particles in the middle of the pipe have the highest velocity, which can be twice the average velocity of the fluid as a whole. The result of the frictions in laminar flow is a velocity profile that can vary from a very flat shape to a parabolic shape depending on the rheological behavior of the fluid, the pipe diameter, and the rate of flow. Turbulent flow regime. A fluid flow regime characterized by swirling or chaotic motion as the fluid moves along the pipe or conduit. The linear velocity of the fluid particles is similar regardless of position in the conduit, although the particles close to the conduit walls have a lower velocity. This characteristic makes turbulent flow an efficient flow regime for the pickup and transport of solids. Turbulent flow is a more effective method for mud removal. It's also the way that sand is transported in slick water. Shear rate. The velocity gradient measured across the diameter of a fluid flow channel, be it a pipe, annulus, or other shape. Shear rate is the rate of change of velocity at which one layer of fluid passes over an adjacent layer. As an example, consider that a fluid is placed between two parallel plates that are 1 centimeter apart. The upper plate moving at a velocity of 1 centimeter per second, and the lower plate fixed. The fluid layer at the lower plate is not moving, and the layer nearest the top plate is moving at 1 centimeter per second. Halfway between the plate, a layer is moving at 0.5 centimeter per second. The velocity gradient is the rate of change of velocity with distance from the plate. This simple case shows the uniform velocity gradient with shear rate v1 minus v2 over h, which I believe in the illustration to the right would be r. Yes. Yeah, I made no real attempt at consistency here. Shear stress. The force per unit area required to sustain a constant rate of fluid movement. Mathematically, shear stress can be defined as tau equals force over area, where tau is shear stress, F is shear force, A is area acted upon by the shear force. If a fluid is placed between two parallel plates placed 1 centimeter apart, and a force of 1 dyne is applied to each square centimeter of the surface of the upper plate to keep it in motion, the shear stress in the fluid is 1 dyne per square centimeter at any point between the two plates. Viscosity. Viscosity is a property of fluids and slurries that indicates their resistance to flow, defined as the ratio of shear stress to shear rate. Viscosity can be expressed mathematically as follows. Mu equals tau over gamma, where tau is shear rate, tau is shear stress, gamma is shear rate, and mu is viscosity. Poise is a unit for viscosity equivalent to dyne seconds per square centimeter. Because 1 poise represents a high viscosity, 1/100th of a poise, or 1 centipoise, is used for mud measurements. 1 centipoise equals 1 millipascal second. Viscosity must have a stated or an understood shear rate in order to be meaningful. Measurement temperature must also be stated or understood. Viscosity is a function of the solids content in the fluid. The more solids, the higher the viscosity. The importance of viscosity. Viscosity is important for proppant transport. There is a minimum viscosity necessary to transport proppant. Usually this is considered about 100 centipoise at 100 reciprocal seconds shear rate. Viscosity is important to friction pressure. Unnecessarily high viscosity wastes the fluid material made, and it wastes the pumping power, since you need to apply more force to pump the fluid downhole. Classification of fluids. In laminar flow, the fluid can be thought of as a series of parallel plates moving at slightly different velocities. By measuring the shear stress at different shear rates, the fluids can be correctly defined and behavior can be accurately predicted. Fluids can then be divided into two major categories, Newtonian and non-Newtonian. A Newtonian fluid is the simplest thing. The fluid is said to be Newtonian if its viscosity only varies in response to changes in temperature or pressure. A Newtonian fluid will take the shape of its container. Under constant temperature and pressure conditions, the viscosity of a Newtonian fluid is the constant proportionality, or the ratio, between the shear stress that builds in the fluid to resist flow and the shear rate applied to the fluid to induce flow. The viscosity is the same for all shear rates applied to the fluid. Water, sugar solutions, glycerin, silicone oils, light hydrocarbon oils, air, and other gases are Newtonian fluids. In this case, you see tau, shear stress, equals mu, the viscosity, times change in velocity over change in r. Here would be distance. Yes. Yeah, that would be shear. Yeah. So shear stress is equal to viscosity times shear rate. Because it is constant, viscosity can be determined from a single measurement of shear stress at one shear rate. Non-Newtonian fluids. Unlike a Newtonian fluid, which displays liquid behavior, a non-Newtonian fluid has properties of a liquid and of a solid. Under certain conditions, a non-Newtonian fluid flows as a liquid, and under other conditions it exhibits elasticity, plasticity, and strength similar to a solid. Unlike Newtonian fluids, the viscosity of many non-Newtonian fluids varies with shear rate. 4 classes of non-Newtonian fluids depends on how the viscosity varies in response to the duration and magnitude of applied shear rate. Thixotropic fluids decrease viscosity over time under shearing. For example, solid honey becomes a liquid after continuous stirring. Rheopectic fluids increase viscosity over time under shearing. For example, cream will thicken after continuous stirring. Pseudoplastic fluids decrease viscosity with increasing shear rate. These fluids exhibit shear thinning behavior. For example, ketchup will squirt through a hole in a bottle top at a high velocity, but stand still as a dollop on a plate. Dilatant fluids increase viscosity with increasing shear rate. These fluids exhibit shear thickening behavior. In the Bingham plastic model, flow will not begin until the shear stress attains a minimum value, the yield stress, after which the flow is similar to that of a Newtonian fluid because the viscosity is constant and does not vary with shear rate. Power law and Herschel-Bulkley fluids describe pseudoplastic behavior in which the slope, the viscosity, of the shear stress versus the shear rate curve decreases as the shear rate decreases. To the right, you will see an illustration of Newtonian versus non-Newtonian effective viscosity. The Bingham plastic fluid model is a two-parameter rheological model. It can be described mathematically as follows. Tau equals yp plus pv of gamma, where tau is the shear stress, gamma is the shear rate, yp is the yield point, pv is plastic viscosity. Fluids obeying this model are called Bingham plastic fluids and exhibit a linear shear stress, shear rate behavior after an initial shear stress threshold has been reached. Plastic viscosity is the slope of the line and yield point is the threshold stress. The yield point or threshold stress is the y-intercept. Examples of Bingham plastic fluids include cement slurries and certain muds. We see over here a linear line indicating a Newtonian fluid, but it does not begin at the origin, it begins higher on the y-axis. This is the yield point. Yield point and then a constant viscosity. The Bingham plastic fluid model. Okay. Plastic viscosity is a parameter of the Bingham plastic model. Plastic viscosity is the slope of the shear stress over the shear rate line above the yield point. Plastic viscosity represents the viscosity of a fluid when extrapolated to infinite shear rate on the basis of the mathematics of the Bingham model. High plastic viscosity is caused by a viscous base fluid and by excess colloidal solids. Apparent viscosity is the viscosity of a fluid measured at a given shear rate at a fixed temperature. In order for a viscosity measurement to be meaningful, the shear rate must be stated or defined. In the Bingham plastic rheology model, apparent viscosity is 1/2 of the dial reading at 600 rpm using a Model 35 viscometer. The power law fluid is generally considered the best model for fracturing fluids. This is a fluid described by the two-parameter rheological model of a pseudoplastic fluid, or a fluid whose viscosity decreases as shear rate increases. Water-based polymer muds, especially those made with xanthan gum, fit the power law mathematical equation better than the Bingham plastic or any other two-parameter model. Power law model fluids are like Newtonian fluids in that they have no yield stress, and they do not develop gel strength in a static condition. This means that the fluid begins to flow as soon as stress is applied to the fluid. Power law fluids can be described mathematically as follows. Tau equals K times gamma to the power of n, where tau is shear stress, gamma is shear rate, n is a specific exponent, and k is consistency. Because of the exponential relationship, a log-log plot is necessary to analyze a power model fluid. Alright, there we see an illustration of a log-log. X is N, and then K is consistency index. Gel strength. It is the minimum stress required to shear a fluid at a measurable shear rate. This means that when this stress is applied, the gel structure is destroyed and the fluid thins down again. The force required to accomplish the breakdown of gel structure depends on time. The longer the fluid is allowed to stand, the greater the force that will be required to destroy the gel structure. The shear stress is measured at a low shear rate after a mud has set quiescently for a period of time, about 10 minutes and 10 seconds, 10 seconds and 10 minutes in the standard API procedure, although measurements after 30 minutes or 16 hours may also be made. Right, you have high flat, progressive, and low flat gel strengths. Low flat is what we want in muds. The consistency index is a rheological property of matter related to the cohesion of the individual particles of a given material, its ability to deform, and its resistance to flow. When the log of shear stress is plotted against the log of shear rate, the resulting straight line curve will intersect the shear stress axis. This point of intersection is the consistency index, log K prime. This value gives an indication of the fluid viscosity and is measured in pounds-foot per second power n per foot squared. The consistency of cement slurries is determined by thickening time tests in accordance with API recommended practice 10b and is expressed in Bearden units of consistency. Behavior index is the slope of the line formed by the plot of the log of shear stress against the log of shear rate. It describes the degree of fluid deviation from Newtonian behavior, a dimensionless value. In mathematical terms, log of tau equals log of k plus n times log of delta v over delta r. The closer that n prime is to 1, the more Newtonian in behavior is the fluid. Therefore, the behavior index is described as a degree of deviation from Newtonian behavior. If n prime is equal to 1, the fluid is purely Newtonian. If n prime is greater than 1, the fluid is said to be dilatant, or shear thickening. Dilatant fluids are not normally encountered in oilfield fluids. If n prime is less than 1, the fluid is described as shear thinning, or pseudoplastic. This means that as shear rate increases, viscosity decreases. Herschel-Bulkley fluid. This is the best law for cement slurries. It's a fluid described by a 3-parameter rheological model. A Herschel-Bulkley fluid can be described mathematically as follows. Tau equals tau sub naught plus k times gamma to the power of n, where tau is shear stress, tau sub naught is the yield stress, k is the consistency factor, gamma is the shear rate, n is the flow index, a power law exponent. The Herschel-Bulkley equation is preferred to power law or Bingham relationships because it results in more accurate models of rheological behavior when adequate experimental data are available. The yield stress is normally taken as the 3 RPM reading on a Model 35 type viscometer, with the N and K values then calculated from the 600 or 300 RPM values or graphically. This followed by a power law type behavior. Okay, determining fluid parameters. The fluid parameters we need to obtain are shear stress, shear rate, and gel strength. A coaxial viscometer, such as the Fann 35, is commonly used to determine the rheological properties of fluids such as cement slurries, drilling muds, spacers, and fracturing fluids. In a coaxial viscometer, rotational speed is proportional to shear rate, and bob deflection is proportional to shear stress. See the illustration, you have a cup here with fluid inside. Inside the fluid is a bob. The bob is attached to a shaft. That shaft is attached to a torsional spring, and there will be a dial here you can't see. The Fann 35 viscometer, also known as a direct indicating viscometer, an instrument used to measure viscosity and gel strength. The direct indicating viscometer is a rotational cylinder and bob instrument. Has two speeds of rotation, 300 and 600 RPM, are available in all instruments, but some are 6 or variable speed. It is called direct indicating because at a given speed, the dial reading is a true centipoise viscosity. Bingham plastic rheological parameters are easily calculated from direct indicating viscometer readings. The plastic viscosity equals 600 on the dial minus 300 dial, and the yield yield point equals the 300 dial minus the plastic viscosity. Gel strength is also directly read as dial readings in oilfield units of pounds per 100 square foot. Right, you see a little illustration of a Fann 35 viscometer. Switch, motor, a gearbox, knob to change gears, little port to read the dial. This is a heating cup, inside of which you have a sample, a rotor, and here's the real deal. This is not a heating cup, this is just a regular cup. You can see a rotor inside. Now, in the 6-speed model, which is the most common, the speeds are 3, 6, 100, 200, 300, and 600 RPM. Use of the 3 and 6 RPM settings may give erroneous readings due to the effect called wall slippage. The rate of rotation at these speeds is too slow to give accurate measurements and should, well, I don't know if should not be used is right, but just be aware. Additionally, recent studies by API have shown that at 600 RPM the results are not very reproducible, which is partially due to cement particle migration. For this reason, use of the 600 RPM setting, I don't know about, I don't know about should be avoided, but you should be aware of that. Maybe be avoided. In cementing fluids, a 6-speed model viscometer will be used to measure rates at 100, 200, and 300 RPM. Now, there's also a 12-speed model. For power law fluids, the exponential curve is more pronounced at low shear rates, and a 12-speed viscometer with speeds of 12, 30, and 60 RPMs is strongly recommended. Yeah, I've used these. They are much better. For all fluids, the 30 and 60 RPM readings should be used because they correspond to a shear rate range that the fluid will encounter during operation in large casing sizes.
Instrument Company's Model 35 viscometer, the standard of the industry. The Model 35 is used around the world to determine the viscosity of drilling fluids and wherever viscosity measurements are needed. It is a true coaxial cylinder rotational viscometer. Such viscometers have been produced by Fann Instrument Company for over 60 years. Viscosity is a measure of the shear stress caused by a given shear rate. It works like this. A measured sample of fluid is placed in the cup, and the stage is raised, lifting the cup. Precision gearing allows the rotor sleeve to rotate at known speeds. The viscous drag exerted by the fluid creates a torque on the bob. This torque is transmitted to a precision spring where its deflection is measured on a dial. The Model 35 is designed for the viscosity in centerpoise to be indicated on the dial with the standard R1 rotor, B1 bob, and F1 torsion spring at 300 RPM. Viscosities at other speeds may be measured by using multipliers of the dial reading. The shear rate may be changed by changing the rotor speed and the rotor bob configuration. Model 35 viscometers are equipped with factory-installed rotor sleeve, bob, torsion spring, and a stainless steel.
Alright, using a Model 35 type viscometer. Here are the steps for using a viscometer to determine the fluid properties of a given fluid. Place a sample of the fluid in the cup of the viscometer. Run the Fann 35 at 300 RPM, 200 RPM, and 100 RPM for 20 seconds at each setting. Record the bob deflections, signified by the Greek letter theta, in degrees. Plot the deflection versus RPM. Compare the resulting graphical representations of the fluid with the rheological models to determine the rheological model, Newtonian, Bingham plastic, or power law, and then calculate the fluid parameters. Right, you see a more detailed diagram of the Fann 35, your 350 milliliter cup, your rotor, it spins, you have a hollow bob attached to the shaft, torsion spring up there, the lens where you can look in and see the dial. Alright, yeah, there's a sample fill line on the cup, and there is a, where is it? Yeah, there's a scribed line on the rotor. They indicate where the fluid should rest. Going higher than that, you can damage the shaft. Operating a Model 35 viscometer. On a 6-speed, to select the desired speed, set the speed switch located on the right side of the base to the high or low speed position as desired. Turn the motor on and move the gear shift knob located on the top of the instrument to the position that corresponds to the desired speed. The viscometer gear shift knob may be engaged while the motor is running. Read the dial for shear stress values. In a 12-speed, to achieve the broader testing range from 0.9 RPM to 600 RPM, an additional gearbox shift lever is used. After preparing the instrument for 12-speed testing by setting the gearbox shift lever, select the proper speed range with the speed shift switch. Turn on the motor and set the gear shift knob on top of the instrument. On the top of the instrument. Okay, I'm not going to read these off. I'll let you pause the video and make flashcards if you want, or something. You can write this down. Measuring gel strength on a Fann 35. The common method is to stir the sample thoroughly at 600 RPM, set the gear shift knob to the 3 RPM position, and then turn the motor off. After the desired wait time, turn the motor to the on position at low speed. Read the dial at the moment the gel breaks as noted by a peak dial reading. The gel strength units are in pounds per 100 square foot. An alternative method is to stir the sample thoroughly at 600 RPM, turn the motor off. After desired wait period, turn the gel knob slowly counterclockwise. Read the dial at the moment the gel breaks as noted by a peak dial reading. The gel strength units are pounds per 100 square foot. Shear stress and shear rate correction. Each spring, bob, and rotor used in the viscometer has a specific number to identify it. These numbers are used to accurately determine the relationship between the angle of deflection with the shear stress and the rotations per minute with the shear rate. It is important to note the number for the spring, bob, and rotor, and use these numbers during calculation. Right, using different rotors or bobs will change the shear rate. Using different springs will change the angle of deflection for a given shear stress. Bob deflection and shear stress. Bob deflection can be used to determine the shear stress, tau, of a fluid. Shear stress, tau, is equal to the angle of deflection, theta, as read off the viscometer, multiplied by the spring correction factor, multiplied by 100 for oilfield units, or multiplied by 47.88 for SI units, in pascals. So, for oilfield units, you'd have tau equals deflection times the spring factor times 100 equals pound-foot per 100 square foot. Determined by comparing the spring number with the bob number on a spring correction factor chart, such as this. Again, you can write this all down. Shear rate. Rotations per minute can be used to determine the shear rate. Delta V over delta R equals RPM times alpha, where alpha is equal to 4 pi over 60 times rotor bob ratio squared over the rotor bob ratio squared minus 1. The rotor bob ratio is determined by reference to the chart position corresponding to the numbers of the bob and rotor, as seen below. So the default is R1, B1. Fluid properties. We can calculate the fluid properties for any fluid that has been tested with a viscometer using the angle of deflection recorded from the viscometer for each RPM setting. The correct spring correction factor and rotor bob ratio, for the number of the spring, bob, and rotor that we are using. Newtonian viscosity calculation. The Newtonian viscosity in centipoise may be read directly from the dial when the viscometer speed is at 300 RPMs and the rotor bob torsion spring combination is R1, B1, F1. Other springs may be used provided the dial reading is multiplied by the F factor, the spring constant, to calculate the viscosity. To calculate the Newtonian viscosities in centipoise with the Fann viscometer, use the following equation. I forget actually what this little eta is eta. Eta n equals S times Q times F times C, where S is the speed factor, Q is the dial reading, F is the spring factor. S is the speed factor. Did I say spring factor? F is the spring factor, and C is the rotor bob factor. And eta n is the Newtonian viscosity in centipoise. Plastic viscosity and yield point calculation. Using R1, B1, F1 combination, test a sample at 600 RPM and record the dial reading. Change the speed to 300 RPM and record the dial reading. And apparently I did not go through and proof my presentation. Determine the plastic viscosity and yield point using the following equations. Plastic viscosity represents the slope of a straight line between the two dial readings. Yield point represents the theoretical point at which the straight line, when projected, will intercept the vertical axis. Plastic viscosity in centipoise equals the dial reading at 600 minus the dial reading at 300. The yield point in pounds per 100 square feet is equal to the dial reading at 300 minus the plastic viscosity, where Q is the dial reading. The power law model calculation. Power law calculations are made from the following information: the behavior index, N, which is the slope of a straight line curve, the consistency index, K, which is 10 to the power of I times CF over alpha to the power of N prime. The intercept I of the behavior index with shear stress when the logs of rotation per minute equals 0. Alright, changing the rotors, bobs, and torsion springs on a Fann 35. The R1B1F1 rotor bob torsion spring combination is standard for all Fann viscometers. Other rotor bob combinations may be used, provided shear rates are calculated for the fluid being tested. Rotor bob combinations other than R1B1 have large gap sizes. As a result, the shear stress dial readings are not consistent with readings from a smaller gap. Rotor removal and replacement on a Fann 35. To remove the rotor from its socket, twist the rotor clockwise and gently pull it down. To replace the rotor, align the rotor slot and groove with the lock pin in the main shaft socket. Push the rotor upward and turn it counterclockwise, locking it into position. So, and pull down. That pulls this pin out of this little slot or groove. Is this slot? This is the groove? Alright. To replace the rotor, align the slot in the groove with the lock pin, then push upward and lock into place by turning counterclockwise. Bob removal and replacement. The bob shaft end is tapered and fits into a matching tapered hole in the bob. Clockwise and gently pull the bob, twist it clockwise while pushing up. Torsion spring removal and replacement on a Fann 35. Remove the dust cap. Loosen the set screws about 1/2 turn. The spring can now be lifted out. Be careful not to stretch the spring. That's true. I stretched the spring once. It was not good. Insert the new spring, making sure the bottom mandrel is properly oriented and seated. Set screw D should line up with the point at which the spring leaves the bottom mandrel. A notch cut into the upper end of the bottom mandrel will help locate this point. Tighten set screw D so that it presses against the split ring to hold the bottom mandrel of the spring. Before tightening the set screw C, make sure that the top of the adjustable mandrel is flush with the top of the clamp E. You may need to slightly compress or stretch the spring to accomplish this. Tighten the set screw C. The slot in the top of the adjustable mandrel should line up with its clamping set screw C. Loosen the set screw F to 0 dial under index, then rotate knob G as required for alignment. Adjust the knob vertically to allow the spring to be clamped in a free position, neither stretched nor compressed. Tighten the set screw F and replace the dust cap. Fann 35 calibration check. A calibration check only verifies the instrument's correct mechanical operation, its torsion, springs, bearings, and shafts. Changing the rotors and bobs only reconfigures the geometry of the shear gap. These changes do not affect the torsion, springs, bearings, or shaft. Therefore, calibration is not required when changing rotors or bobs. Periodically, the Model 35 should be checked for proper calibration. If the measurements do not meet the specified accuracy, then the viscometer should be calibrated or repaired. Calibrate the Model 35 weekly while Deadweight calibration of a Fann 35. Remove the rotor and the bob. Be sure that the tapered end of the bob shaft is clean, and then install the calibration spool. Install a calibration fixture by clamping it onto the upper portion of the Viscometer support legs. Select a weight. Insert the bead at the end of the thread into the recess in the top of the calibrating pool. Wrap the thread a little more than once around the spool and then drape the thread over the pulley. Hang the selected weight on the thread and then adjust the calibrating fixture up or down until the thread from the spool to the pulley is horizontal. If necessary, adjust the torsion spring. The factory tolerances for F1 spring are only 127 plus or minus half a degree for 50 grams and 254 plus or minus half a degree for 100 grams. A movement of plus or minus half a degree is permissible when the main shaft is turning. This movement will generally be dampened out when the fluid is being tested. Check the linearity of the dial reading with at least 3 weights. If the spring appears to be non-linear, then the bob shaft is probably bent. An instrument with these characteristics needs additional service and/or repair.
The Model 35 should generally be calibrated every month or when repairs or adjustments have been made. This is important to ensure that the machine is always producing the most accurate results possible. Perform these steps to calibrate with the deadweight calibration kit. First, remove the rotor and bob. Install the calibration fixture and spool. Select a weight according to the dial deflection for calibration weights. This can be found in Table 6.1 in the Model 35 manual. Next, attach the weight to the unit, then adjust the alignment of the weight. The string should be horizontal from the spool to the pulley. Once complete, compare the dial reading to the information in Table 6.1 in the manual. When determining the results of the calibration, the factory tolerance for an F1 torsion spring is 127 plus or minus a half degree for 50 grams and 254 plus or minus a half degree for 100 grams. A movement of plus or minus 1/2 degree is permissible when the main shaft is turning. This movement will generally be dampened out when fluid is being tested. If necessary to obtain the required calibration, adjust the torsion spring as specified in a later section.
Fluid calibration check on a Fann 35. Make sure that the instrument is clean before immersing the rotor and bob into the calibration fluid. If necessary, remove the rotor and thoroughly clean the bob, bob shaft, and rotor. Make sure the bob shaft and rotor are straight and have not been damaged. The batch number on the label of the calibration fluid must match the batch number on the viscosity and temperature chart. Fill the sample cup to the scribed line with calibration fluid and place it on the instrument stage. Elevate the stage so that the rotor is immersed to the proper immersion depth. Place the thermometer in the sample cup until it touches the bottom, and then secure it to the side of the viscometer to prevent breakage. Operate the instrument at 100 RPM for approximately 3 minutes. This will equalize the temperature of the bob, rotor, and the fluid. Read the dial at 300 RPM and 600 RPM. Record these numbers and the temperature from the thermometer to the nearest 0.1 degrees Celsius, or 0.15 degrees Fahrenheit. The viscosity at the 300 RPM reading should be within 1.5 centipoise of the viscosity from the temperature chart at the recorded temperature. Divide the 600 RPM reading by 1.98. Compare this value to the value on the chart. The viscosity at the 600 RPM reading should be within 1.5 centipoise of this viscosity value. Plot the 300 RPM reading and the 600 RPM reading, then draw a straight line from 0 through these 2 points. If the 300 and 600 points do not fall in a straight line, it is possible that either the rotor, bob, or bob shaft is bent, or that other eccentricity exists. Points at 100 RPM and 200 RPM can be plotted if verification is needed.
The Model 35 should generally be calibrated every month or when repairs or adjustments have been made. This is important to ensure that the machine is always producing the most accurate results possible. The calibration fluid check uses only certified Newtonian fluids. All calibration standards are certified by methods traceable to the United States National Institute of Standards and Technology. Fann calibration fluids are available for separate purchase. Make sure the instrument and its components are thoroughly cleaned before immersing the rotor and bob into the calibration fluid. Also ensure that the bob shaft and rotors are straight and have not been damaged. Perform these steps when using the calibration fluid check method. First, fill the sample cup to the scribed line with the calibration fluid and place it on the instrument stage. Then elevate the stage so that the rotor is immersed to the proper immersion depth, as noted by the scribed line. Place a thermometer into the sample cup until it touches the bottom, and then secure it to the side of the viscometer to prevent breakage. Operate the instrument at 100 RPM for approximately 3 minutes. This will equalize the temperature of the bob, rotor, and the fluid. Record the temperature and dial readings at 300 and 600 RPM to the nearest tenth of a degree Celsius or 1500ths of a degree Fahrenheit. Results should be within plus or minus 1.5 centipoise of the viscosity value on the fluid chart at the recorded temperature noted. Note, it is important to first divide the 600 RPM reading by 1.98 prior to comparing the results to the fluid chart. Readings outside the specified limits are indications that the instrument should be either calibrated or repaired. After the calibration check, carefully wipe clean the rotor surfaces, including the inner and outer portions, as well as the bob, thermometer, sample cup, and work area.
Torsion spring calibration on a Fann 35. Make sure that the bob shaft is not bent before adjusting the torsion spring. Remove the dust cap A and then loosen set screw C about 1/2 turn. Insert the calibration tool into the spring, which is a special tool you have to purchase, and rotate the adjustable mandrel inside the spring slightly. Turn the mandrel counterclockwise if the dial reading is too low, or turn the mandrel clockwise if the dial reading is too high. Tighten the set screw C. The slot in the top of the adjustable mandrel should line up with the clamping set screw C. Before tightening set screw C, check the top of the center mandrel to be sure that it is flush with the top of the clamp E. To accomplish this, it may be necessary to adjust the spring by slightly compressing or stretching the spring. Loosen the set screw F to zero the dial under index. Then rotate the knob G as required for alignment, then adjust knob G vertically to allow the spring to be clamped in a free position, neither stretched nor compressed. Tighten the set screw F and replace the dust cap A.
The Model 35 should generally be calibrated every month or when repairs or adjustments have been made. This is important to ensure that the machine is always producing the most accurate results possible. Follow these steps to adjust the mechanical torsion spring. First, remove the dust cap, then loosen the zeroing sleeve set screw by 1/2 turn. Insert the calibration tool into the spring and rotate it to slightly adjust the mandrel. Tighten the set screw and ensure that the mandrel is flush with the clamp. Loosen the spring bushing set screw and adjust the zeroing sleeve accordingly to zero the dial. Tighten the spring bushing set screw and replace the dust cap.
Measurement and precision. Alright. Measure the temperature of the fluid being tested according to the manufacturer's specified procedure, which shall be traceable to a national or international standard such as ISO. Everything needs to be traceable to ISO. Everything. Temperature shall be measured to an accuracy of plus or minus 1 degree Celsius, or plus or minus 2 degrees Fahrenheit. pH shall be measured to an accuracy of 0.1 units. All other quantitative measurements shall be made to an accuracy of plus or minus 2%, unless specified otherwise. Fluid preparation. During all procedures, steps shall be taken to minimize entraining air into the fluid. That's to say, while blending it, make sure the vortex does not go too deep into the blending blades, and then it can touch the top of the nut just barely, but it can't actually enter into the blades, because then you'll start entraining air. Following preparation, all fluids, except those intended to be used as fracturing fluids, shall be filtered through a filter of pore diameter of 2 microns. The procedure used to prepare the fluid sample shall be documented, including the following information: description and/or composition of the base fluid. Preparation of the fluid shall be described, starting with the fluid source, such as deionized water, tap water, completion brines, produced water, seawater, or type of oil. In something like produced water, it's also important to note where the water was produced. Identification of mixing apparatus, container volume, and total volume of fluid prepared. Identification of each fluid component and amount added. The order and method of addition for each component. Mixing speeds with time at each speed. Aging or holding time prior to measurements if required. Temperature. pH for aqueous fluids. All other aspects of the fluid preparation which are known to affect the outcome of the viscosity measurement, such as filtration of completion fluids. Now, I normally pronounce but most people seem to say aqueous. That doesn't make much sense to me, since this is from aqua. But whatever makes you more comfortable. Calibration shall be carried out using a standardized Newtonian calibration fluid, traceable to an international or national standard such as ISO. Generally, one will use polydimethylsiloxane, aka dimethicone. Calibration oil viscosity shall be selected to encompass the shear rate and shear stress envelopes to be evaluated. Measure the rotor or sleeve speed according to the manufacturer's specified tachometer calibration procedure, which shall be traceable to a national or international standard such as ISO. So, that is to say, you will need to occasionally check the RPMs using a tachometer, and that tachometer needs to be verified by an ISO certified verification service. Certify your tachometer with certified ISO certification specialists. Preparation. Rotor and bob shall be properly aligned. That seems self-explanatory, but whatever. All parts in contact with the fluid shall be self-evident, not self-explanatory. All parts in contact with the fluid shall be at the same temperature as the fluid. The vertical space between the bottom of the bob and the bottom of the vessel shall be at least 13 millimeters or half an inch. After being placed in the viscometer, the fluid is stirred for 10 seconds to 15 seconds at the highest shear rate for which the measurement is to be made. Viscosity measurements should be made from lowest to highest shear rate. Record the average reading 20 seconds after the reading is stabilized at each shear rate. After each test, do the following. Take off the rotor and bob, clean each piece with soap and water. Wipe off the shaft with a damp cloth in a down motion. Do not press against the shaft up motion. Up motion will push fluid up into the shaft. Reassemble the unit, ensuring that each piece is finger tight.
The Model 35 should generally be calibrated every month or when repairs or adjustments have been made. This is important to ensure that the machine is always producing the most accurate results possible. Perform these steps to adjust the dial. Unscrew the dust cap and set it safely to the side. Using an Allen wrench, unscrew the set screw spring bushing by a half turn. Then look down at the dial and adjust the zeroing sleeve as necessary. Once properly aligned, gently retighten the set screw. Finally, place the dust cap back on and tighten all the way down. These tips are recommended for properly caring for the viscometer. Clean the bob and rotor after each test. Periodically examine the bob and rotor for dents, abrasions, or other damage. Always remove the bob from the bob shaft when transporting the instrument to avoid bending the bob shaft. Periodically test the bob shaft bearings. This is done by operating the instrument at 3 RPM or 6 RPM without a sample and observing movement of the dial. It should not move more than plus or minus 1 division. Rough bob shaft bearings should be replaced. And finally, oiling or greasing of the viscometer is not required in normal service. Running a test with the Model 35 is a straightforward and simple process that will be demonstrated in the following video. But first, let's go over a couple of basic principles. To start the test, add 350 milliliters of pre-stirred sample to the stainless steel sample cup. The sample cup has a line that marks 350 milliliters. Next, immerse the rotor to the proper immersion depth, as indicated by a scribed line. Damage to the bob shaft bearings may occur if this immersion depth is exceeded. If other sample holders are used, the space between the bottom of the rotor and the bottom of the sample holder should be 1/2 inch or 1.27 centimeters or greater. Also, remember that it is important to not adjust the 12-speed gear lever while the motor is running, as this may cause severe damage to the motor. The Fann 35 viscometer, or rheometer, is used to measure shear stress due to the resistance of fluid flow at various shear rates, measured in RPM. The viscometer operates at 6 speeds, ranging from 3 RPMs to 600 RPMs. To select the desired speed, set the speed switch to high or low, then move the gear shift knob to the position that corresponds to the desired speed. To prepare for testing, line up the slot and groove on the rotor sleeve with the locking pin on the shaft collar, then push upward and turn counterclockwise to lock into place. Pour the sample into the thermo cup to within about 1 inch from the top. Insert a thermometer into the hole in the thermo cup. Secure the cup by making sure the 3 pins on the bottom of the cup are properly locked into the stage. Raise the stage until the fluid reaches the scribed line on the rotor sleeve. Heat the sample to the desired temperature while shearing at a constant 600 RPMs. When the fluid is close to the desired temperature, immerse the thermometer into the fluid and wait until the desired temperature has been reached. Once reached, reduce the heat to stabilize the temperature. To obtain the 600 RPM reading, the speed switch should be in the high position and the gear shift knob should be all the way down. Wait for the pointer to stabilize and record the dial reading. To obtain the 300 RPM reading, reduce the rotor speed by moving the speed switch to the low position and keeping the gear shift knob all the way down. Wait for the pointer to stabilize and record the dial reading. To obtain the 200 RPM reading, reduce the rotor speed by moving the speed switch to the high position and pulling the gear shift knob all the way up. Wait for the pointer to stabilize and record the dial reading. To obtain the 100 RPM reading, reduce the rotor speed by moving the speed switch to the low position and keeping the gear shift knob all the way up. Wait for the pointer to stabilize and record the dial reading. To obtain the 6 RPM reading, reduce the rotor speed by moving the speed switch to the high position and moving the gear shift knob to the middle position. Wait for the pointer to stabilize and record the dial reading. To obtain the 3 RPM reading, reduce the rotor speed by moving the speed switch to the low position and keeping the gear shift knob in the middle position. Wait for the pointer to stabilize and record the dial reading. To measure 10-second gel strength, stir the sample at 600 RPM for approximately 10 seconds to break the gels. After 10 seconds, set the gear shift knob to the 3 RPM position and move the speed switch to the off position. Wait 10 more seconds, then turn the speed switch to low and record the dial reading at the maximum deflection. Gel strength units are pounds per 100 square feet. To measure 10-minute gel strength, stir the sample at 600 RPM for approximately 10 seconds to break the gels. After 10 seconds, set the gear shift knob to the 3 RPM position and move the speed switch to the off position. Wait 10 minutes, then turn the speed switch to low and record the dial reading at the maximum deflection. To measure 30-minute gel strength, stir the sample at 600 RPM for approximately 10 seconds to break the gels. After 10 seconds, set the gear shift knob to the 3 RPM position and move the speed switch to the off position. Wait 30 minutes, then turn the speed switch to low and record the dial reading at the maximum deflection. This test is complete.
Now this has all been about the standard Fann 35, but if you want something a little higher quality, many companies make digital versions that are electronically controlled instead of purely mechanical, that can be attached to a computer. In addition to the Fann 35, we have what are called the Model 50 rheometers. Model 50 type refers to a standardized design for a high pressure, high temperature rheometer, as opposed to the Fann 35, which can only operate at ambient pressure and at temperatures of up to 200 degrees Fahrenheit. The original such, the industry standard was the Fann Model 50. These rheometers possessed pressurized sample chambers of up to 2000 psi, interchangeable springs like the Fann 35, interchangeable bobs like the Fann 35, a continuous adjustable speed between 2 and 1000 RPM, up to 450 degree Fahrenheit temperature capability. Procedure for using those, the Model 50 type, you preheat the thermal bath to test temperature. Within a space of 45 seconds, you must load the fluid to be evaluated into the viscometer immediately after the last component is added according to the mixing procedure. Place 52 milliliters of fluid into the viscometer. Pressurize the system with nitrogen to a minimum of 2.75 megapascals or 400 psi and immediately start shearing at 100 reciprocal seconds. When shearing of the fluid starts, define the elapsed time as 0 and begin heating the fluid. At 20 minutes elapsed time, the fluid temperature shall be no lower than 5% below and no higher than 3 degrees Celsius or 5 degrees Fahrenheit above the desired test temperature. At 30 minutes elapsed time, and for the remainder of the test, the fluid temperature shall be within plus or minus 3 degrees Celsius or plus or minus 5 degrees Fahrenheit of the test temperature. Fluid shall be sheared at a constant 100 reciprocal seconds initially and between shear rate ramps. The time reported for each shear rate ramp is the total time elapsed when the ramp begins. Starting at t equals 20 minutes, shear rate ramps shall begin every 15 minutes up to 2 hours and 5 minutes. Beginning at 2 hours 35 minutes and continuing up to 4 hours and 5 minutes, ramps shall be every 30 minutes. After 4 hours and 5 minutes, the elapsed time when ramps begin is at the discretion of the operator. However, these shall be reported. The specified shear rates for all shear rate ramps are 25 reciprocal seconds, 50 reciprocal seconds, 75 reciprocal seconds, and 100 reciprocal seconds. The shear rates during a ramp shall occur in that sequence, but the sequence may be either increasing or decreasing, and it is a good idea to actually have the sequence run twice in each direction. First decreasing from 125, then increasing back up to 100. Following each change in shear rate, the fluid shall be allowed to equilibrate for 25 seconds. This is followed by 5 seconds of data collection. Each new shear rate shall be attained when the first 5 seconds following completion of data collection at the previous shear rate. A 40-second equilibration period shall be allowed before collecting data at 25 reciprocal seconds. Shear rate during a shear rate ramp. Record the viscosity data at least once per second and report the arithmetic average of the data obtained. At all other times, report viscosity data at least once per minute. Rheology test reporting. You need a lot of information when you report on the test you've done. The test report should include at least the following information: the date, your name, your lab's name, your fluid, is it non-cross-linked, is it cross-linked, is it viscoelastic surfactant, the fluid application, is it fracturing or whatever, the base fluid data, the source of the base fluid, if it's aqueous, whether it is deionized water, field water, or seawater. If it's field water, again, you want to note its source. The water pH, if it's a hydrocarbon, which one? If it's an acid, what acid is it? You have to document the mixing, the manufacturer of the blender, the model number, the container volume, and the final fluid composition preposition and preparation. The volume mixed, the filtration criteria, the mixing procedure, the components, the amount of each component, aging or holding time prior to measurements, the fluid temperature, the fluid pH, the fluid mixing speeds with time at each speed, shear history data, so data about any shear history simulation, the fluid temperature, information about the viscometer, what type it is, the rotor bob, the spring factor, the spring constant, the calibration date, all measurements and all calculations for the test. You have to document the procedure. For a single point measurement, you have the shear rate and you have viscosity at time and temperature. For multi-point measurements, a shear rate ramp, you have elapsed time at the beginning of the ramp, increasing or decreasing shear rates, shear rate between ramps, apparent viscosity at 40 reciprocal seconds and 100 reciprocal seconds, power law parameters, K, N, R squared, viscosity and fluid temperature versus elapsed time. Thermal melting and shear degradation. This is something you will see in a test that run on a Model 50 type viscometer, rheometer. This is a normal over time due to temperature or shear effects. And here on the green line, or the blue line, either one, you'll see jumps in viscosity as the shear rate drops for each ramp. That's normal behavior. I've reversed indices in the test shear ramp. To say, you have a shear ramp, the first one is normal, the viscosity increases, just like in the previous slide. Then, the next ramp you see the viscosity decreases. That is the cratering. Cratering is an indication that the fluid is close to failure. Fluid properties at low shear rates are divergent from the model behavior. That's what I mean. This is the model, this is divergent. Bob climb is another problem. In bob climb, viscous fluids can climb up the bottom shaft of the Viscometer. See that happening here. This is a frac fluid-like mixture of boric acid and guar. Yes, so this is called the Weissenberg effect, and this obviously interferes with the test. In this picture, you'll see a normal frac fluid in blue. You have an initial increase in viscosity, and then gradual degradation. This, whatever brown frac fluid, is not the same over here, but initially we have this strange stuff when it's the highest viscosity, and this is caused by the bob climbing. Overcrossing, another problem. You get a high initial viscosity here, as you expect. Then there's an immediate drastic drop in viscosity, followed by a slow decrease. Now that slow decrease is the normal degradation we see. But what we're seeing here is syneresis. When the gel overcrosslinks, the gel network actually squeezes water out of the gel. That water layer forms between the gel and the sides of the rotor cup or the sides of the bob, so that the gel does not adhere to the walls of the container and slides against it, so you're getting a much lower reading in response to the shear rate. Low crosslinker concentration. Essentially, you don't get the crosslink you need, and this happens. Low initial viscosity, no increase on heating. This, generally speaking, when the fluid heats up, the crosslinker is activated. Here are Model 50 type rheometers. Industry leader, the Fann Model 50. This actually is obsolete. It's not really used anymore. And other companies have made superior versions. My favorite is the Chandler 5550. Another common one is the Grace. I don't recommend the Grace. It is very delicate. You end up doing a lot of maintenance on that. And I have not used Ophi's machine. But so these are usually used for crosslink gel breaking tests. You need to calibrate these weekly. And I'm not going to give you a detailed procedure on using these the way I did with the Fann, because this has already been an hour and 15 minutes. So if you have one of those machines, you'll have a manual. You can look in that. Anyway, thank you for tolerating me.
The Model 5550 Viscometer represents the state-of-the-art in viscosity measurement, with easy maintenance, simplified operation, and the most precise measurement available in the market. The Model 5550 Viscometer uses industry-standard API Couette geometry combined with a digital torque measurement with fully integrated data acquisition and control software. Precise temperature control is achieved through our unique carbon block heater. This exclusive heater design replaces outdated oil bath technology, improves safety, and makes it ideal for offshore applications. With easy access to internal components, the replacement of the 5550 bearings can be accomplished in a matter of minutes.
I'm not trying to show for Chandler. I just wanted a video that would give you a good look at
the position of the torque measurement system, coupled with a highly effective climb arrestor, keeps viscous fluids from exiting the shear gap, enabling a more accurate viscosity measurement. Chandler Engineering designs and manufactures